Okay, question number 2 here is saying the diagram below shows an object P suspended from a ceiling with the aid of 3 light strings X, Y, Z connected at point O, right? The first question there is saying define the term resultant vector. That's our first question. So we are defining a resultant vector as a single vector having the same effect as 2 or more vectors together, or we can say it is the vector sum of 2 or more vectors. Okay, let's go to 2.2. Draw a closed vector diagram to show all the forces acting at point O. Indicate the 2 angles in your diagram. Indicate 2 angles in your diagram. Right, so I want to use this question to explain how do we draw a vector diagram. And as a matter of fact, a closed vector diagram, as a matter of fact, a closed vector diagram is produced when an object is at equilibrium or when an object is stationary, meaning to say when the force is acting on an object, the resultant force is equal to 0, when F net is equal to 0. Right, so at O, let's first identify. Look at Y, starting at O here, the direction of Fy, the force in Y, we can call it Ty to be precise. It's a string, so the force that is acting through it is tension. So we can call it Ty if we want to, but I will call it Fy, no problem. Right, so Fy, what is the direction of that Fy? It is going in this direction. Right, let's talk about the force acting through X, which is also a tension. Right, so it's going in this direction. From O, mind you, it's going from O, so it's going in this direction. That's apparently our X, Fx, the force through X. Then, lastly, the force through string Z from O, it's going downwards. You can see from the point O here, the force is acting downwards. So we have Fz acting downwards. There is our Fz. Okay, so these are the forces we have and their appropriate directions. That's very important. Now, when you draw a closed vector diagram, you are simply co-joining these 3 forces, but you have to draw them, each force, you have to draw it at the head of the other or the previous force or the force that you started with. Like, for example, I'm now drawing the closed vector diagram. If I start with Fy here, this is the direction of Fy apparently, right? Now, when I now join with Fz, Fz has to be drawn at the head of Fy, but in the correct direction that is following. Remember, Fz is going downwards, therefore it has to be drawn going downwards. Now, when I now draw Fx, I am now drawing Fx from Fz towards Fy. That will mark my Fx. That's how you simply draw the vector diagram, the closed vector diagram. So in simpler terms, it's as if you are simply taking these 3 forces and you are joining them together to form a triangle, but each force has to be drawn from the head of the other towards the specific direction that it is initially following. Right, so that's our closed vector diagram. Alternatively, in whichever way, say for example, I started with Fx or with Fz. Let's assume I'm starting with Fz. There is my Fz there, right? Now, I will now draw the next force, which is Fy, from the head. There we go. So it doesn't matter which one am I starting with, as long as it's following the correct direction that it's supposed to follow, you will still be correct. Then, there we go. Now I'm now drawing Fx from the head of Fy, because I last drew Fy. So I am now drawing Fx from there, going towards the specific direction that is following. You can see now a vector diagram is being produced. Right? How about the angles? And I need us to just know that right at the point here, there is another easier way of trying just to bring out the forces, right? If I close here like this line that I'm just showing you, as it is produced going downwards, that's Fz there. This angle that you see here, this angle, is the angle between Fz and Fy in your closed vector diagram. Same applies, this angle that you see here is the angle between Fx and Fz. Okay, assuming, say, for example, the angle had not been given. Suppose that angle there had not been given as it is right now. How are you going, say, for example, you have this angle here. Say this angle is 30, assuming it's 30 degrees. How was I going to find this angle here? What you simply do is you draw a line here. Then you will know that this 30 is equal to this angle 30 degrees. Why? Because these are alternate angles. Angles between parallel lines, the horizontal and the roof or the ceiling are forming parallel lines. Right? So hence for that reason, this one becomes 30 and the other one becomes 30, which means this whole angle here, this angle that I'm marking, is actually 90 degrees. That has to be known because it is the angle between the vertical and the horizontal. So it's basically 90 degrees. So if I say 90 minus 30, I will then find this angle. Why are we interested with it? Because this angle is the angle between Z and Y. Apparently, it is also the angle between Z and X. Often, it's always like that. On a closed vector diagram, you can easily bring it out like that. Okay, so I now know the angle between Fx and Fz is 30. The angle between Fz and Fy is 60. I can now bring it into my closed vector diagram. Again, the angle between Fx and Fz, we are saying is 30. The angle between Fy and Fz, we are saying it's 60 degrees. So that's basically how we are bringing it out. Okay, so automatically we can now find the remaining angle. How? By saying 180 minus 60 here, subtract 1 to be 9 times. We are now dealing with them. It's good to bear that in mind as you proceed further. Okay, so there are many ways of drawing a vector diagram. You can draw it in whichever way. Just make sure that you are maintaining the directions that the forces are initially following. Okay, I think I have explained in a much easier way there. Let's go to 2.3. 2.3 is saying using, so the instruction they were saying indicate two angles. Indeed, I ended up indicating more than two, but when in exam, just indicate two. It's enough. So just there, I did it for illustration purposes. For more emphasis sake, I ended up producing all the three. Like use the vector diagram, question 2.2, to identify the string that exerts the largest force on point O. So the instruction is saying use the vector diagram. So we want to use the vector diagram that we have, any one of them. Okay, number one, the length of the arrow simply indicates the magnitude of our force. So the longer the arrow, the greater the magnitude, always. So you are trying to identify between Fy, Fz, and Fx, which one has the longest line or the longest arrow. Right? So in our case here, because we have a right angle triangle, always the angle opposite the right angle is the biggest, is the largest always. Why? Because it is the hypotenuse. Hypotenuse is the Greek name for longest side. So it means that in our case here, we are just trying to identify which one is the hypotenuse, which angle, which side, sorry, is opposite the right angle. Apparently it's Fz. It's Fz. So Fz is the longest side. Fz is the largest force. In what sense? Because it is the longest side, which is represented by the longest side on our closed vector diagram. So because of that, it is the biggest or the largest force. Right. So let's answer the question now. Using the vector, identify the string that exerts the largest force on the point O. It is Z. So the string is Z. Give a reason. It is because Fz is opposite to the largest angle, since the length of the side of the triangle indicate the magnitude of the force. So we are simply saying it is Z because on the closed vector diagram, Fz is the longest side as it is the opposite, the biggest angle, the 90-degree angle, right? Let's quickly go to the next question. It's saying calculate the magnitude of the force X and the force Y. Right. Given that the mass of the object P is 0.25 kg. So the first thing that we are to do is we shall calculate W, the weight. So we will calculate the weight, right? What do we get? Weight is equal to mass multiplied by gravitational acceleration, of course. So we have been given the mass there, 0.25, multiplied by the gravitational acceleration, 9.8, and that will give us 2.45 Newton. Right, so we have the gravitational force weight. Now that we have the gravitational force, we can relate now with our diagram. Looking at P, we have the gravitational force of P, which is in 2.45. Apparently, it is equivalent to Fz because at P, as always, since P is also stationary, it means that forces acting upwards are equal to forces acting downwards. Therefore, it means Fz. So we are simply saying Fz is apparently also equal to W, is also equal to weight, which is equal to 2.45. So Fz we have 2.45 Newton. Now, if Fz is 2.45 Newton, it means that using our closed vector diagram here, it's our hypotenuse. So considering now our diagram, it means it's very much possible to find Fx first by saying, remember, this is a right angle triangle, right? So since it is a right angle triangle, and now we are saying Fz, we have it, is 2.45, and this is our hypotenuse, and the Fx is the one we are looking for, and we have an angle here of 30 degrees. We can simply say Fx is equal to Fz multiply by cos 30. What are we doing? We are using the trig ratios. So, right? We can use that to identify the size of Fx on our right angle triangle. So our Fz, we have it is 2.45. Remember, it is the same as the weight of P. That's 2.45 multiplied by cos 30, which is equal to 2.12172339, which is to two decimal places, 2.12 Newton. Alternatively, we could have said, and we're still going to be correct, Fx is equal to Fz multiplied by sine 60. Sine 60, why? Because as we consider 60-degree angle now, it means this is opposite and this is the hypotenuse. Fz will always be the hypotenuse. So which ratio is opposite the hypotenuse? It is the sine ratio. Hence we can say 2.45 multiplied by sine 60, and we can now find our values. Right. So we can now find our value, which is 2.12 Newton. Again, we can still arrive. So that's Fx for us. Let's go to Fy, the force at y. Fy, considering again the right angle triangle we are saying Fy is equal to Fz cos 60, right? Because as we consider the 60-degree angle, it is the adjacent and this is the hypotenuse. So hence we can use the cosine ratio, right? So we can say 2.45 multiplied by cos 60, and that gives us 1.225, which we can round off to decimal places as 1.23 Newton will still be correct. Or we can say again, Fy is equal to Fz multiplied by sine 30, right? Considering the right angle triangle we have there. So it's equal to 2.45 multiplied by sine 30, which will still give us the same result. 1.225 to two decimal places becomes 1.23. All rows, they still lead to wrong. We would have arrived again. So basically, it's another way again of calculating it. And as it stands, it is the last question in this question. So we can quickly go to the next question. Okay, the other question we have here is saying two forces of magnitude 50 Newton and 80 Newton act at a point on a Cartesian plane in the directions shown in the diagram. Okay, so the question is saying, give the correct term for the following description. That's the first question we have there. It's saying a single vector having the same effect as two or more vectors together. We just made that in the previous question. That's the definition for a resultant vector. So apparently, that's a resultant vector there. So we have just given the correct term. That's 2.2 for 2.1 for us. We have just answered it. Let's go to 2.2. 2.2.1 is saying calculate the magnitude of the vertical component of 50 Newton force. So we want the magnitude of the vertical component of the 50 Newton force. So we'll call it F Newton force. So we can even call it FY50 or F50Y. It's still okay, no problem, right? How do we calculate it, right? The easiest way of identifying the vertical and the horizontal component of a force is when a force acts diagonally, move following the Cartesian plane, the horizontal dimension and the vertical dimension. It doesn't matter which one you start with. If I start with the vertical, I will go in this direction until I am aligning with the 50 Newton force. So this is my Fy, the vertical component of the 50 Newton force. Then, as I go now towards the head of my diagonal force, my force that is acted diagonally, this is now my horizontal component. So it doesn't matter which direction have I taken, even if I go in this direction, from the tail to the head, I'm going until I align with the head. This marks my Fx, the horizontal component. Then as I resume or as I continue from the head of my horizontal components towards the head of my actual force, this marks F1, right? So it means the vertical component can be calculated. So let us calculate the vertical component together, right? How do we calculate it? Fy is equal to, so always it's equal to F multiplied by sine theta. If theta is an angle to the horizontal, like right now, 30 degrees is an angle to the horizontal, right? But if our angle was here at this point, we were going to call it the angle to the vertical. Apparently, that's not what it is. So this is an angle to the horizontal. So we know that the vertical component has to be given by this formula here, right? So we can now substitute 50 multiplied by sine 30, and we will end up having 25 Newton. That's Fy 50, the vertical component of the 50 Newton force. Okay, let's go to 2.2.2. It's saying calculate the magnitude of the resultant net force. Right. In order to find the resultant net force R, we need first the sum of the horizontal component. We call it Rx. We want also the vector sum of the vertical components, which is Ry. Then we now add them vectorially using Pythagoras theorem. So let's first find Rx. How do we find Rx in this case? We need also Fy. We have just calculated, we need Fx, sorry. We have just calculated Fy, the vertical component of our 50 Newton force. We now need Fx, the horizontal component of the 50 Newton force. Why? Because it is the one acting in the same dimension with the 9 dimension, right? As a matter of fact, it's very good to note the syllabus tend to confine us to these two dimensions, the horizontal and the vertical dimensions, so much it wants us to understand them, to know them. So it's good to relate, to always know that how do we calculate Fx now, right? So here is our Fx. Fx is equal to F times cos theta. So it's good to also always know again, when theta is the angle to the horizontal, Fx shall be given by that formula. The horizontal component of the force shall be given by that. So we can simply say 50 that we already have multiplied by cos 30, right? So 50 times cos 30, it gives us that's 43.30270192 two decimal places. That is 43.30, right? That's 43.30 which is the same as 43.3, right, Newton. Right. So in calculating Rx, therefore, the resultant for the vector sum of the horizontal components, right, Rx shall be given by, right, 80 is already in the horizontal dimension. So we will simply say 80 minus 43 minus, why subtracting? And yet we are saying vector sum because they are acting in opposite directions. The 80 Newton and the 43.3, they are acting, remember, the 43.3 Newton is this Fx. And from this diagram, you can see that it's acting towards the left. That's where it is going. And the 80 Newton is going to the right. So choosing right as positive, 8 will be positive and the Fx will be negative. So we are adding a positive vector and a negative one. So hence, because of that, we end up subtracting and we will get 36.7. So that's 36.7 Newton, right? We have found Rx. The next thing is to find Ry. So we now want Ry. Ry is equal to, right, in our case, do we have any other force acting in the vertical dimension except Fy? In this case, we do not have any other. I'm trying to talk about all the forces that are acting, right? You can notice that the only force that is acting upwards will become Fy. Hence, because of that, Fy is equal to Ry. So we will simply say Fy, Ry is equal to Fy is equal to 25 Newton. We have already calculated it, right? So therefore, R is equal to the square root of Rx squared, right, plus Ry squared, which apparently is equal to the square root of 36. Okay, that's 36.7 squared there, plus 25 squared, and that will give us 44.41 Newton to 2 decimal places. We've arrived, right? So that's 2.2.2 for us. The next question there is saying calculate, okay, it's saying calculate the direction of the resultant net force. Calculate the direction of the resultant net force. So we want the direction. All right. In order to find the direction, we find it on the vector diagram, right? Or we can just use the vector diagram of our diagram, that our information that we have there. Okay, we have R, X, and Ry, right? Which directions are they acting? Right, Rx first, we saw that when we took right as positive, right, it means the moment we say 8 Newton, when we were adding, it means 8 was positive. Why? Because right was positive during that time. And the moment we said minus the Fy that we had, 43.3, I'm talking about this calculation that we did here. Again, right as positive, which means Rx here is acting to the right. This is to the right. That's the direction it is taking. That's why it is positive when also the 80 was positive. And yet the 43.3 was negative. This one was acting to the left, this one was acting to the right. So it means this is to the right. Right. So Rx is to the right. Okay. So there is our Rx. Now, if Rx is acting to the right, it means that the direction that it is taking is this one. There is our Rx. Now let's go to Ry. Ry apparently has no choice. It is equivalent to Fy, so its direction Fy is acting upwards. So it's also acting upwards. How do we know it's acting upwards? We did when we were indicating that Fy, the force, the vertical component of the 50 Newton, is acting upwards. Is acting upwards in whichever direction, it's still acting upwards. So because of that, Ry is also acting upwards. So we have our two forces, Rx and Ry. They are acting in these directions. right? So if that is the case, then we are saying this is Rx, and apparently this is Ry, right? Where is R? Right? What you simply do is you tend to complete forming a rectangle, right? Then you say the diagonal of that rectangle. There it is, right? Don't join head to head. It's wrong. Start at the starting point here, right at this point. Then as you go, that marks the direction of R. So if this is your R, what you now want is basically the angle. Which one? This angle here. So you can calculate this angle as your theta, or you can calculate this angle. It doesn't matter. It doesn't matter which angle have you calculated. Right. So I'm going to calculate this angle here, right, in order to indicate the direction. So what is the size? Apparently, this is Rx. This is R. But we have their sizes now. Rx, we said is 36.7. Ry, we say it is 25 Newton. Hence, for that reason, we can use turn ratio because this is opposite and this is adjacent, right? Because this is a right angle triangle, mind you, right? So, because of that, we can perform our calculation directly with knowledge. Tan theta is equal to opposite over adjacent, which is R, right? So theta is equal to arctan of Rx, which we know that's 36.7 over Ry, which is 25, right? So arctan of 36.7 over 25, that gives us 55.74 degrees, right? Which means this angle here is 55.74 degrees. So even this one can be found as well, because this whole angle is 90 degrees, don't forget. So because it's an angle on a right angle triangle and apparently in a rectangle as we have indicated there. Right? So we can subtract to get this angle 90 minus 55.74. We end up having that's in 13. That's actually 34.26, punching that on the calculator, right? So if this is our angle, it means we have arrived. We can write it really as how we can indicate the direction using bearing. We can write it as north 55.74 degrees east, or we can say east 34.26 degrees north will still be correct, right? So, or we can say it's just 55.74 degrees clockwise from the positive y-axis will still be correct again to say that. So that's our question there. That's how we were supposed to calculate the direction as well as all the given information. Let's go to the other question. Next question here is saying, a pulley system is used to keep a heavy object at rest as shown on the diagram below. So 2.1, it's saying, define the term resultant vector. So the resultant vector as usual, a single vector having the same effect as two or more vectors together, or a vector sum of two or more vectors. So I think from the previous questions, it's now clear and obvious that the resultant vector, if ever it is to be asked, it becomes clear on how you are to define it. Right, let's go to 2.2. Draw a vector diagram showing the forces acting on the object. Label the forces and indicate the angles on your diagram. Right. Number one, let's first identify the forces, assuming we have a free body diagram. Right. We have a force acting towards this direction. That's the 1,440 Newton force. Right. We have another force acting towards this direction. Remember, from the heavy object, right? That's the 1,284.95 Newton force. Then we have the gravitational force acting downwards. That's, we are saying separately, there is weight acting downwards. We can be sure on that. There is the 1,440 Newton force acting towards this direction. That's the 1,440 Newton acting in this direction. There is the 1,284.95 Newton force acting towards this direction. 0.95 Newton force acting towards this direction. These are the forces and their respective directions. So when you are now drawing a vector diagram, you are simply co-joining these forces to form a triangle, making sure that whichever force you start with, when you now draw the next force, you are drawing it from the head of your previous force. Okay, so let's do it for a specific force to start. You can start with any of the forces. So it makes the drawing of the velocity vector diagram to become much more easier. Okay, so what if I want to start, let's say, with the 1,140 Newton force? So I'm going to start with the 1,140 Newton force. Okay, there it is. So that's the 1,140 Newton. Okay, right at the head, I now draw the weight, the gravitational force. There it is. That's my gravitational force there. Okay, from there, I now draw the 1,284.95 force. So there I draw it. There it is. Right. That marks 1,284.95 Newton force. Right. These are the forces we have. Was this the only way? Okay, there were many ways actually. Let me try to bring out another way we could have just drawn it. Okay, assuming this time around, we are going to start with the gravitational force, the weight. Suppose we want to start with the weight. Okay, there is the gravitational force, the weight. Okay, right at the head of the weight, I can now draw the 1,440. There it is. There it goes. That marks the 1,440 Newton force with its correct direction. There it is. Okay, right at the head, I now draw the other force going towards the direction of course, I have to complete this part here. Okay, pardon my diagram here is a little bit poor. We have to do that, especially with a ruler, so that your lines can be straight. Okay, that marks the 1,284.95. Make sure you are accurate with the digits there. Right, guys. If you notice now what has happened, if you check these separate forces that we drew initially, are you noticing that their directions are still maintained on any of these two closed vector diagrams that I've drawn? The weight is still going downwards in whichever way, in whichever diagram, in which any of the diagrams that I've drawn. 1,440 Newton is still acting in the same direction that it was acting in the same direction. The 1,284.95 is still acting in the same direction. So that's basically how you do it. Okay, let's just answer. So the question was saying, label the forces and indicate the angles on your diagram. So this is important again, as an easier way of identifying the angles, right? At the point here, where the heavy object is, right? We are saying, if I extend this line, if we happen to extend it, this angle here that you see is the angle between the 1,440 Newton force and the weight. This particular angle here. Same applies. This angle here, the 40 degrees we have been given, is the angle between the weight and the 1,284.95 Newton force. This is the angle between them. So on my diagram, it means it becomes clearer now to identify, okay, this is where the 40 Newton is. The angle between the weight and the 1,284.95 force, that's the 40 degrees, right? So how about this thing? How can I find it? Okay, it's easier to find. What I can simply do is this whole angle, this one that I'm marking right now, this one is 90 degrees. So if it is 90 degrees, If I say 90 minus 55, I get 35, which means this angle is 35 degrees. So that's apparently the angle we have. This one, it's 35 degrees, right? So that's how we can indicate the angles in our closed vector diagram. That's 35 there. Okay, so in whichever way, look at this now that the angles are known. We are saying the angle between weight and the 1,285. This is the angle. We said the angle between the weight and the 1,284.95 is 40 degrees. There it is 40. The angle between the weight and the 1,440 degree angle is 35. There it is 35 degrees, which means the remaining angle here can be found how? By saying 180 minus 40 plus 35, right? And we can now find the remaining angle. So it becomes 105 degrees. So this angle here is 105 degrees. That's how we identify all the angles there, right? So wanting to indicate all the angles, we can indicate them that way. Okay, the next question is now saying calculate the weight. Now, in calculating the weight, we have two options: either using the closed vector diagram we've created, or basically using the understanding that the object that is in question here is at rest. So since it is at rest, it means forces acting upwards, talking of the forces in the vertical dimension, forces acting upwards are equivalent to the forces acting downwards. Which forces are acting upwards? We have, of course, the vertical component of the 1,284.95 force and the vertical component of the 1,440 Newton force. So considering that, right, it means if this is the 1,440 Newton force, this is its horizontal component and this is its vertical component, right? These are the two force components we have for that particular force. Same applies, it also follows that for the 1,284.95 force, this is its horizontal component, and apparently this becomes its vertical component, right? So we will call this one F1, and I will call this one F2, right? So for my F1, right, it's just a way of wanting us to understand what I'm going to do. So F1 vertical, which we are calling F1Y. F1Y, remember we called the 1,440 Newton force the F1, right? So F1Y plus F2Y should be equal to the gravitational force weight. Why? Because force is acting upwards, because F net really is equal to 0. So since F net is equal to 0, this force is the sum of this force is equal to 0. So W, the weight becomes negative because we are acting up, or we are taking upwards as positive, right? So basically they are equal. These forces are equal to the force acting downwards, which apparently is only weight. Weight is the only force that is acting downwards, right? So this is an equation we have formed. Now, how do we find F1Y? F1Y is equal to F1, the 1,440 Newton, multiplied by sine 50, to be given by F vertical, Fy is equals to F sine theta, where theta is the angle to the horizontal. Right? So in our case, we also need this. So we can say F1 sine 55 plus F2 sine, in this case, it's sine 50. So sine 50 is equal to weight, right? So we can substitute 1,400, right, plus 1,000 sine 50 is equal to our weight. That on the calculator, we get to 2 decimals. It's one way of doing it. Vector diagram. And it's not a non-right angle triangle. What can we use? We can use our weight, which is known. Either the sine rule or the cosine rule. The onus is on us, where we can say A over sine A right, is equal to B over sine B, since we are looking for a side. So we'll say weight, the side we are looking for, over sine of the angle opposite the weight, which is sine 105, right, is equal to, I now take the side and the opposite that are facing each other. So I will say 1,440 is equal to 1,440 over sine, which angle is facing 1,440? Apparently, it is the sine 40 degrees, which is this angle here, right? So apply. So weight sine 40 is equal to 1,440 sine 105. Then I divide by sine 14. We proceed with understanding of calculations. I would just want us to know that here I could just multiply sine 105, then multiply by sine 105. We are done. We would have reached this point here, 1,440 sine 105, right, divided by sine 40, to identify things or ways of arriving quicker at the answer without actually losing your marks. So here we are. So we can punch this on the calculator. We will still get 2,163.91 Newton. So there are many ways of killing a cat. We can still arrive in many ways. We can still arrive to calculate that weight. Okay. So this marks